So moving on to our last presentation today. I've got my notes here. Let me find it. So our next presentation is from Alex Hall and Fran Kremer, both from US EPA. And Alex is an expert in data analysis and geographic information systems. And Fran serves as a senior scientist both at the US EPA Office of Research and Development, ORD. I think they're both in Cincinnati. Today they're going to talk about the work that they've done to look at private domestic well locations. Margaret mentioned the 90 census. Well, they found a way to use that information and some newer information to come up with some better numbers and the potential impacts that has on contaminant sources and climate change. So thank you for joining us, Alex and Fran.
Today, I think building on some of the earlier comments that we've heard today, and in particular, Jackie's emphasis on environmental justice and how we look at the EJ issues relative to private domestic wells and water supplies in general, and as well, Reem and Megan's presentation looking at the wells and contaminant sources specific to Chesapeake Bay. So we're going to bring this up to a national level to run through some of the approaches that we've taken to improve the estimates on private domestic well location. And again, as Steve just mentioned, we built this on the 1990 census data and subsequent data in terms of housing surveys. And then lastly, related to the driller log data that we have available by state. So we're going to walk through that, and then subsequent to that, we're going to look at a different array of contaminant sources and how we think about those sources of contamination, and ultimately then how does climate change impact the quality of our wells. So we'll cover just walking through this and giving you some background on how we've come up with the most current estimate on the private domestic densities application that's available free for use, and then as well other sources, including septic systems and CAFOs, on mining and superfunds and RCRA facilities, as well as storage facilities for oil and hazardous substances, and then more locally looking at potentially the impacts of road de-icing. And then lastly, looking at the approaches for considering climate change and what the potential implications are for private domestic wells and how we need to be thinking about climate change relative to this water source and supply into the future.
Thanks, Fran. And I'm exhausted just hearing about all the things we're going to talk about today already. But I'll start by talking about our effort to estimate where private domestic wells are nationally. And specifically, I want to talk about how we did it and why we did it. The previous speaker said correctly that we haven't had a good estimate or census since 1990 on where our private domestic wells are located nationally. It was asked in the long form census in 1990 and hasn't been asked since. And we want to know where this is because of all the contaminants Fran just kind of rattled off there. There's a lot of things that can affect our wells, and we need to know where our wells are to know, what the co-location of contaminants in our well geography, right? So that's kind of why we sought to update our kind of national picture, and you see it here on the screen, of our well universe. And how do we do this? Well, we went in with an assumption. We assumed that in 1990 and going forward, the rate of well use remained constant over time. So if you're in a community and 50% of that community is on wells and 50% are not on wells, we assume that domestic ratio remained consistent over time. It was a theory, and with that theory, we can update our well estimates based on housing unit change. So here I list two methods we use in estimating 2010 private domestic wells. The NHU method here at the bottom, basically we just looked at the domestic ratio in the census for all 11 million census blocks, and we looked at the housing unit change over time, and we just assumed the same ratio, and we got an estimate on 2010 based on the housing unit change. Well, we wanted to test our assumption, right? Is that static state of domestic ratio the correct assumption? So we tested it. We went out to all 50 states and we gathered the driller logs. And so we did that. And what we did is we found 20 states that had really good driller logs from 1990 to present with really good geolocations. And for those 20 states, we did like an additive process. We started at the 1990 as a baseline. We added the driller logs from 1990 to 2010. And we compared our estimates, right, between our assumption, the NHU model, to this more empirical model based on actual real data. And what did we find? The scatter plot on the right there shows the relationship between our housing unit model and our well estimate model on the x-axis. And you can see that in a lot of states we do very good, in the R squared of the 90s. I think globally, I think we had an R square of 0.97. So there is a very good relationship between housing unit change and just wells drilled. So great. So we can use the NHU model nationally, and we can really estimate how many private domestic wells there are. And then, so on the left here, we can see the number of private domestic wells by state. And we can show in gray and black are the two different models. California is first with, little over 1.5 million, followed by Florida and Michigan. And you can see the gray and the black bars are very similar, very close to each other, which is good. Which is what we wanted to see. So we did all this for all 11 million census blocks, so 220,000 block groups, and we have some takeaway messages. So in 1990, we found that there were 15 million housing units in private domestic wells. Now, from our method, our study, we found that in 2010, there's 23 million housing units relying on private domestic wells, or 52.6 million people. That's 17% of the population. Now, this is higher than a lot of other estimates. The USGS had some estimates, but we're pretty confident in this data because it was based on empirical driller logs. So that's kind of the landscape of the private domestic wells. And this map here shows also the change in wells over time. In 1990, the brown areas are showing areas where we lost private domestic wells, and then the blue areas are areas where we gained private domestic wells. So I'm going to show you a web map that we have that can be accessed publicly by anybody that kind of shows this data. You can go and look at where your private domestic wells are located. So here it is. And we're displaying the data a couple different ways. Here we're looking at private well density, number of housing units on private domestic wells per kilometer, right? And a couple of things stick out. You can see this kind of ring around major metropolitan areas, the suburban rings around Atlanta, Charlotte, Indianapolis, where you've got the public water infrastructure in the middle, and then a lot of people and a lot of wells on the outside. Here we're looking at the data by census block group. We can zoom in and get kind of a more granular picture of the data. So that's by block group. And now we're looking at by census block. So these are block estimates. And here you can clearly delineate the public water infrastructure of Charlotte. So this really isn't good for estimating private domestic wells, where they are, but also where they're not, right? So
hey, Alex.
Yeah.
We're still seeing your slide. We're not seeing.
Oh, thanks.
All right.
You can see both my screens. Thanks for letting me know. So yeah, this is the map, and here we're looking. So appreciate the heads up. So here's the data. We're looking at it by private domestic well density, and like I was saying, you can see the kind of the urban rings around major cities. And this is density. So right, well, housing units per square kilometer on wells. We can zoom in closer somewhere, and we can get a more granular view. These are the census blocks, and as I was saying, we can see the public water infrastructure area, and then also where the private domestic wells are. We can see this data in a couple different ways. Here's by density. We can look at it by just well count. Right, so here the count of private domestic wells from 0 in white to 75 or more in dark blue. Or we can look at it by the population served. So the black areas here represent 100% of the population is on private domestic wells, where white is 0%. So I think this is a good resource. It's really the most up-to-date and most granular kind of national picture of where our wells are, where people are getting their well water from. So wanted to share that with you. And thanks for letting me know to share it with you on the right screen. And I'll throw it to you, Fran. And you're on mute.
Okay, yeah, thank you. So moving then now into looking at some of the potential contaminant sources now that we have this kind of geospatial data and resolution on private domestic wells, it certainly enhances our ability to think about a variety of contaminant sources. And so just to briefly off the top in terms of looking at some of the setback distances that we think about for private domestic wells and different sources, certainly CDC has provided information, as well as American Academy of Pediatrics, and in particular because of the issue of nitrates and methemoglobinemia. So they're looking at generally then the setback distances to protect those wells. But I think as you'll see moving forward through the slide deck and ultimately thinking about climate change, I think for this community, it's also worth further discussion to think about these setback distances in particular with regard to changing environments and changing conditions that we have in many of these locations. And then secondly, with regard to the density of some of the private domestic wells we find in given communities, these setback distances are especially important.
So I'm going to kind of start off the discussion on contaminant sources to our drinking water infrastructure by starting with leaking underground storage tanks. Now, there's been 500,000 leaking underground storage tanks discovered in this country since about 1989. Currently, there's about 62,000 that are in our backlog remaining to be cleaned up. There's like 10,000 active leaking underground storage tanks in Florida, like 6,000 in Michigan, and unfortunately, a lot of where these leaks are occurring are where homes are, and where homes that are primarily on private domestic wells. Now, this map on the right shows the number of private domestic wells within 1,500 feet of all of our active releases, right? So, we see in Florida, we've got about 60,000 private domestic wells, really close by to our underground storage tanks, leaking underground storage tanks. About 30,000 in Michigan, 15,000 in Illinois. So I just wanted to put that on your radar. Fran and I work a lot with this issue of leaking underground storage tanks, and the main receptor or concern for leaking underground storage tanks are private domestic wells. So I just wanted to note that. And so we at the EPA, we didn't have a national database of where our leaking underground storage tanks were located. These are state delegated programs. So we went to all the states and collected their information on leaking underground storage tanks. And here's kind of the geography of that data, right? So every dot on that map represents about 10 square miles. And within that 10 square mile area, how many leaking underground storage tanks have there been historically and currently? And you can see basically every metropolitan area in this country has had between 150 and 1,000 leaking underground storage tanks per 10 square miles. So this isn't a minor issue. And it's really not an issue. I mean, it's an issue that affects pretty much every community. So I just wanted to kind of show you the extent of the issue. Oh, there you go.
And in particular for underground storage tanks, the key components that we're concerned about with regard to water quality in private domestic wells are benzene, toluene, ethylbenzene and xylene, some of the main components of fuel. And just honing in particularly on benzene, which is a potent carcinogen. The maximum contaminant level or the drinking water standard for benzene is 5 micrograms per liter. The typical fuel composition, and this varies depending upon the fuel type, but we're looking generally about 6,000 milligrams per liter. So what this then translates into, if we're looking at the composition of the fuel relative to the drinking water standard, we have to have an attenuation factor of about 1 million really to attenuate that compound before it would reach a well from a leaking underground storage tank site. So that's a big ask. So distance is our friend in this case. The further, obviously, that the fuel spill is from a private domestic well, the better off we are. And then I think bottom line too is thinking about some of the earlier discussions today and the lack of testing that is done. Here for benzene, just as an example, the odor and taste threshold is about 60 parts per million and 4.5 respectively. So we're several orders of magnitude off in terms of the sensory detection of benzene relative to a drinking water standard. So we clearly need to be thinking about the co-location of these sources relative to the private domestic wells.
Yeah, then let me jump in here, and I just want to show everybody a data set that the EPA published on leaking underground storage tanks, just to get a sense. And this is public; it's called US-Finder. You can just Google it. This does not want to cooperate with me. Basically, we can zoom in anywhere in the country, and we can look at where our underground storage tanks are and our leaking underground storage tanks are. This is state source data. And basically what you're looking at, every dot on this map represents an underground storage tank facility. Think they're primarily your gas stations, right? The blue dots there represent active facilities with active tanks. And the light blue ones represent historic sites, but all the tanks have been closed out, but there may be residual someplace. So this is kind of the density of our underground storage tank universe. And then concomitantly, here are our releases. The dark red there represents active leaking underground storage tanks, and then again, the pink are historic leaking underground storage tanks that have been cleaned up. And what's really nice about this tool is we actually incorporated our private domestic well data into it. So if we're looking at releases and we want to know the risk to our private domestic wells, we can go in and kind of query the data based on their potential to affect private domestic wells. So here I can say, show me all the leaking underground storage tank sites around Indianapolis with at least 10 private domestic wells within 1,500 feet. 1,500 feet is kind of the maximum extent of a plume under kind of normal circumstances. So I can click that. And here, every one of these points is a leaking underground storage tank that's currently active or historic that have at least 10 private domestic wells within 1,500 feet. So it's just kind of a way of querying the data and looking at the potential impacts to our wells.
And consistent with that story too is certainly we have a high density of gas stations in suburban and exurban areas, and that overlaid with just the density of private domestic wells in these neighborhoods because of the lack of expansion of the water infrastructure. So it's really this kind of donut effect of the overlay of these systems that are obviously of concern. So now shifting into septic systems, and we heard a bit of discussion about that today in terms of septic systems and potential impacts on our private domestic wells. If we could just go back one slide, Alex.
Sorry. There you go.
And that's okay, if not, no worries. Okay, oh great, okay, thank you. So here it's really site-specific conditions and the groundwater gradients that are of concern, and these are in many cases not considered when the septic systems are installed, as well as the private domestic wells are installed. And generally, it's just trying to configure where's the feasible space just to put in a system for a given plot. Compounding that then, if you have these decisions in an area where the private domestic wells and septic systems are at a higher density spatially, where we're putting the septic system and where that is located relative to the neighbor's private domestic well certainly accentuates this problem. So how we need to think about septic systems and the private domestic wells and the co-location of these systems to prevent contamination, not only of the systems on site, but the private domestic wells that are surrounding these systems and how they function and flow. And so there was some good work that was done by Laurel Schrader et al. In the Cape Cod area, looking at private domestic wells, and in particular considering septic systems as well as landfill leachate sources in this area. They found a variety of contaminants from pharmaceuticals and PFAS, and looking at a range of these concentrations. And compared those to some of the public drinking water supplies. So here again, I think as was demonstrated this morning in Jackie's presentation, even looking at lead, obviously there's differences between the private and public water systems and the concentrations of concern. So here too, this work further exemplifies that. And I note too, in this study, they were using nitrate as a potential screening approach to serve as a representative indicator for an array of organic contaminants. So this is something certainly to delve into further, and certainly from a cost point of view and an analytical point of view, easier to think about relative to a broader array of organics and the associated costs that it would incur for homeowners.
So I want to go back to the 1990 census. Not only did that census ask, where do you get your water source from, private or public sources, it also asks, what are you on a septic system or not? Which really gives us a good, way to look at this co-location of our septic systems and our private domestic wells. Now, any on the map there on the right, any highlighted block, or pink or yellow, represents areas where there's 80% of households using wells and septic within this block groups. And you can see some, spatial patterns here, mainly on the eastern seaboard, the Great Lakes area, and around the Ogallala Aquifer. And basically what we found is, 8.5% of block groups had more than 80% of housing units in wells and 80% of housing units using septics. Yeah, that's 17 million people that get their drinking water source close to their septic systems, right? So I wanted to kind of bring that home. And we're also in the process at the EPA of updating our 2010 estimates to the new 2020 census. So we'll have updated data that reflects the 2020 population shifts. And we're also using the same technique to estimate where our septic systems are. So we get a really current snapshot of this kind of co-location of receptor and potential contaminant source. And I want to just highlight this graph here. And every dot on that map represents a census block. And here we're looking at, within that census block, the percent of the population on septic on the Y, and then the X percent on wells. And you see this kind of barbell distribution. So you've got a lot of block groups in the top right and a lot of block groups at the bottom right, or bottom left. And what that's saying is, if you get your well, if you're in a block group or a community that has a lot of wells, you typically have a lot of septic, right? And if you don't have wells, you typically don't have septic. Now that may be good for the people at the bottom left, but that means that the people at the bottom top right, again, you do have this kind of co-location of receptor and contaminant source.
So looking at nitrate in particular, it's handy just to see in general where we have nitrate drinking water violations nationally. And so the Safe Drinking Water Information System provides this data, and certainly you can obviously get some of this specific to at a state level, but this gives you a broad snapshot of where to think about the prevalence of nitrate, which in turn gives some greater sensitivity to the need to be sampling for nitrate in our private domestic wells.
Then let me just kind of turn to CAFOs. Basically, we're going to be paying attention mainly to North Carolina here. North Carolina is one of the largest states in terms of CAFOs. There's about 9 million heads in that state. There's also 26,000 wells within half mile of a CAFO, right, and 76,000 within a mile. There's also 200. There are 200,000 wells in block groups with a CAFO, right? That's 1.6 million total. And I should just mention this here that in 2001, the Wisconsin Supreme Court ruled that current laws give the state authority to enforce water quality standards for private domestic wells through use of permit conditions for CAFOs. So maybe a legal hook, at least in Wisconsin. Now, what does that kind of look like? And this isn't very surprising. My mouse is not cooperating. This is not going to surprise anybody. Where there's CAFOs, there's going to be wells, right? Because CAFOs are mainly in rural areas. And you can see that the dots on the map there, the colored dots representing the total swine head count. And you can see, a close correlation between where those are and where our wells are, right? With CAFOs, you get, a lot of nitrogen pollution, as well as E. coli, of course, leaching into the groundwater. So just something to keep in mind where, you have a contaminant source that's primarily in rural areas. And those are definitely in areas where we've got our private domestic wells.
So shifting now to some of the mining sources, and again, taking a national view of this issue. In general, we have some 140,000 abandoned hard rock mine features. This is a longstanding issue, particularly in the West and Southwest. There also could be upward of some 400,000 unidentified abandoned mines that are being considered, and this data is coming from the Government Accounting Office report. In particular, there's tens of thousands that indeed may pose specific hazards to those communities. In one study that was a focus on the Navajo Nation, looked at the reliance on the private domestic wells, and in particular focusing on uranium and arsenic mines. And here they found these concentrations at 13 and 15% higher than what would be an acceptable drinking water standard. I think the other major takeaway from just thinking about mines in general and looking at distances for these sources and where our private domestic wells are in these environments where you have fractured environments and preferential pathways, you can get much longer distances for the contaminant to travel and be transported to impact a private domestic well. And indeed, in this case, they found uranium up to 6 kilometers away from the source and found these in private domestic wells. So it's these types of environments, and we have fractured environments, not probably to the extent that a mining operation would provide, but certainly other preferential pathways that can enhance the distances, the transport to contamination. And this here just gives you a general picture, again, nationally, to get a snapshot of the mining features that we're looking at, and certainly for the states that are impacted by these mining sites to think about particularly the metals and looking for concentrations of metals in the private domestic wells.
And then let's just switch to another contaminant source, Superfund sites. This is under the purview of the EPA. And here we're just aggregating the data to the county. But here you're looking at the number of wells within a half mile of Superfund sites, right? And that, again, information is aggregated by county. And, you've got these dark blue areas, you have between, 50 and 1,200 wells within just a half a mile of these very toxic sites. Nationally, there's about, almost 50,000 private domestic wells, and these serve about 100,000 people daily. Sorry about my mouse. Switching gears to landfills. We have different types of landfills. We have construction and demolition landfills, and these are typically unlined landfills. They're not required to have lining on them, which portends to leaching into our groundwater. Within the United States, we've got about 3,000 landfills, and we've got almost 40,000 wells within a half mile of these landfills. You can just kind of look at the spatial distribution of that on the map. It's pretty ubiquitous. We've got landfills in every state. And then let me switch gears to above ground storage tanks. And here we gathered state data on above ground storage tanks. And in particular, we were interested in what's called a Clean Water Act hazardous substance storage tank. Now, the EPA will be soon regulating 297 Clean Water Act hazardous substances that are stored in above ground storage tanks. And these store really nasty stuff. We're talking TCE, benzene, sulfuric acid, and a lot of other carcinogenic and mutagenic substances. Unfortunately, this data is not available publicly on where the location of these tanks and these large above ground storage tanks. Some of them hold between 1 million and 10 million pounds. So here we kind of had to obscure the data, and we were just kind of showing a heat map of where these hazardous substance tanks are located. In red it's like a really dense area, and sparse is in blue. And what's very clear here is this Baton Rouge to New Orleans corridor. That's kind of colloquially known as Cancer Alley, and this may have something to do with it. This is kind of the major petrochemical corridor in the country, as well as like where a lot of our refineries are. And I should say, on any given day, there's about 4 billion pounds of hazardous substances stored on any given day. And every black dot on that map represents 50 people on a private domestic well water. And you can especially see around the Lake Charles area and within this Baton Rouge to New Orleans corridor, you get a lot of people at private domestic wells near facilities that are storing millions, if not billions, of pounds of hazardous substances daily. So unfortunately, this data isn't publicly available, but I just wanted to kind of raise the issue here by kind of showing this kind of heat map of the issue. And then switching gears to road de-icing, and frankly, I didn't think about this much until I stumbled upon this issue. And the USGS kind of publishes this data that you're seeing in the top left of the amount of road salt application. Here we're looking at Pennsylvania, New York, Ohio. And I was pretty stunned at this. The blue areas show an annual road salt application from 300,000 to 1.3 million pounds, right? And even the beige area, which pretty much takes up the entire map, is between 50 and 100,000 pounds. Well, the salt goes somewhere, right? And it's going to go into our groundwater. And there's such a thing as having too soft of water, right? If you want to look at the trends here of de-icer applied, this is in the millions of metric tons. This is a problem that's only increasing, right? We're applying more and more each year, basically. And the problem with this is it can, the bullets here can mobilize other harmful substances such as radon and mercury and lead. It can, increase blood pressure in humans. And, one study, and this is pretty stunning, New York State estimated that 24% of private domestic wells were contaminated with de-icing salt. And 70% of survey participants stopped using their well water because of safety concerns. Now, this is an issue that's mainly in certain geographies in this country, of course, just in colder climates. But from the few studies we have, this can't be a major issue and can definitely impact your private domestic wells.
Okay, so now we're going to shift into more specifics about climate change, and certainly off the top here, looking at drought, and for our colleagues in the West and the Southwest, you're in the throes of this already in the springtime. Increasingly, we see every year now this drought map, and look at this. I mean, these are really extreme conditions that we have not over the years routinely seen at this point in the calendar. And I would just suggest too, you may want to bookmark this site to think about, what the drought means, and certainly relative to wells running dry in the state and local areas, and what this may portend as well with regard to water quality. So anyway, the USGS has come out with some recent data just showing what these declines in groundwater also impacting the quality of the groundwater that remains under these drought conditions. And so while it's already enough for us to think about testing and getting the testing done on the private domestic wells, what these contaminant concentrations may portend with protracted drought conditions certainly can further impact groundwater quality, and yet another reason to think about the temporal testing needs for private domestic wells. And then the next slide, related to the issue of drought too, and thinking about pumping regimes, and back to the earlier slide where we're talking about where septic systems are located and the private domestic wells are located, and the density of the private domestic wells in particular, and how they function in a given community. So as an example here on the left-hand side, the red dots are representing 4 different types of contaminant sources. And you'll see the 2 pumping wells drawing in the wells to the wellhead. And so on the right, changing that pumping regime where a third well that's introduced at a very high pump rate is basically drawing in all the contamination to that well. And again, this is just to work through a scenario, but to visualize for you the need to think about our pumping strategies, the rate at which we're extracting that, and what this means in relative to the contaminant sources that are in proximity to our wells. And then moving to precipitation. So yes, in other portions of the country, we have the opposite problem of the South and the Southwest, and looking at extreme precipitation and the resulting inland flooding that's occurring. On the right-hand side, it just shows you, particularly for the Midwest and the Northeast, the amount of, or the number of extreme precipitation events that are occurring and the increasing frequency of that. This obviously portends to more inland flooding that's going to occur, and certainly these downpours and just the extreme precipitation is increasing across the country, but again, particularly in the Midwest and the Northeast. And so how we think about this and the flooding and the impact on our water quality for our private domestic wells will be increasingly important. And then here as well, looking at groundwater flooding and regional variability in our groundwater levels. On the right-hand side here is actually just some data that's out of Dade County, Wisconsin, as an example. They do a great job in tracking groundwater levels, and you can see what that trend looks like for this specific county. So again, if we're thinking about these groundwater levels increasing, as an example for a septic system. So we're looking at that vertical profile to get some distance between the ground level to the groundwater. So if that groundwater is increasing, we have less of a treatment zone to attenuate the contaminants of concern from those septic systems. And likewise for the private domestic wells, that enhances the lateral transport or movement of those contaminants into the private domestic wells. So these are certainly issues that we're going to progressively need to think more about.
Then let me kind of step back. We'll go back to our underground storage tanks and talk about that. The nemesis for an underground storage tank is really water, right? It causes corrosion, it can foul fuel, it can cause corrosion from both the inside and the outside of the tank. Where there's microbially induced corrosion, you get pitting of the tank and you get these releases, right? And I showed you a map before of our 62,000 leaking underground storage tanks. Now, the one thing that we don't want is our underground storage tanks in water. We don't want them sitting in the groundwater, and we definitely don't want them in floodplains. If they're floodplains, they could be, inundated with water and get inside the tank, causing this microbially induced corrosion. And it can even create buoyancy issues where tanks will pop out of the ground if you have enough water on top of them. So basically, we wanted to look at, how many of our tanks are sitting in water, basically. How many of our tanks are sitting in FEMA's 100-year estimated floodplain? And here's that map of the number of tanks by state. And, you can see that in Pennsylvania, we got about 2,600 tanks. In Texas, 2,200. Altogether, there's about 33,000 underground storage tanks within FEMA's 100-year floodplain. And that's about, 250 million gallons of fuel stored within these floodplains on any given day, right? And so tanks within the floodplain are more likely to have releases, and with these releases, we can, of course, the main receptor is, of course, our private domestic wells.
And then finally, looking at climate change and sea level rise, and how we think about both the integrity of the wells as well as the water quality, with saltwater intrusion in these systems being increasingly prevalent in coastal areas. This will be something we'll need to think about and work with our states and communities in addressing this and forecasting in the next 10, 20 years, especially, where will the water supplies come from? What will be the water quality of these systems? And then likewise associated with this, compounding the sea level rise is just the coastal impacts for these areas. So if you look at just even, for example, in Texas and look at sea level rise, that compounded with, say, the hurricanes, and looking in particular at Hurricane Harvey, there were some 250,000 private domestic wells were inundated by that hurricane. So if you look at that intrusion in these areas, it certainly creates a picture that these communities in particular we need to be paying attention to and thinking about water quality into the future. And just very briefly here from our Office of Water website, certainly the state certified programs and laboratories that are available, and as well our Office of Water has updated a private domestic well site, so you'll find some new links and information that's contained there as well. And then lastly is just for the future, just some contact information for us and additional links here to other sources of information, both on the private domestic wells and contaminant sources. So with that, we'd be happy to answer any questions.
All right. If you guys don't mind, it'd be great to see. Thank you, Alex. So there are some questions here, and I apologize. I'm looking at two screens, and I got caught watching the presentation, and it was moving just like it was supposed to. So it looks like it was almost 8 minutes. we might be able to go in and edit that to at least put the right slides with the right voice, which we will try to do on our end after the conference is over. Okay, so first question here, has it been correlated to determine if the wells were installed into a mineral-bearing formation? Any sampling done prior to the mining activities?
I'll toss to you, Fran.
Oh, I'm sorry. I didn't catch the question. I'm just reading it now. Oh, and in terms of the, if the wells were installed into a mineral bearing formation, these could be, I am myself was not engaged in the study that we reported on, in particular in the Navajo Nation. But I could certainly go back and certainly send you a link to that study and get you additional information.
Okay. And early on, Jackie asked a question about understanding how every well drilled since 1990 is in there. And I think it certainly depends on which state you're working with, how accurate that actually is.
Yeah, I mean, we went and looked at the kind of the state code in which different states required drilling in different times. Some states, early 80s, some states late 90s, early 2000s. The first factor we had to make sure of is that they require drilling post 1990, right? Are we positive that every homeowner alerted the the permitting agency and that they report it? No, but I think because this is work with such large databases, little errors like that, I don't think will tweak the end result. The second thing that we had to make sure of the data is that the geographic coordinates were very precise. Some states map them based on the TLSS system, the kind of gridded system, mainly found in like the Midwest, used in the Midwest. But that's too rough. That's too coarse of a geographic unit. We wanted a GPS lat longs. So we found 20 states that had good reporting since 1990 and had really good geographic information. And thirdly, they had to differentiate between agricultural wells, domestic wells, monitoring wells, and the like. So that we could just look at domestic wells.
And that's probably it's the best you can do, I'm sure there.
Yeah.
So, there were several questions about how do we get the census to begin tracking this again. I don't know if you have any insights there.
Well, I know, Fran, we've spoken to people at the EPA who are have been lobbying for that. But I don't know if you can speak to that anymore.
Well, yeah, and we hope this community, quite frankly, is able to advocate for the need to restore this question in the census data. And obviously that's going to help us over time. But in the interim, this method here at least gives us by the census block the ability to understand the density of these wells. But yes, it would be the ideal world if we had the same information from the 1990 census.
Sure.
Go ahead.
Go ahead.
I was just going to say, so it's on the long form census, right? So and that's given out to about, I think, 30% of the population. And then they, through statistical measures can extrapolate that out the whole population. But yeah, I mean, we're not asking for much, just 30% of the population to answer if they're a private domestic well or not. I think it's worth it.
Yeah, I think everyone would agree it'd be good to understand. The big news, I think, with the paper you published and the work you've done is that EPA's webpage, Fran mentioned, you've updated that. The EPA's number before that was 13 million, and now it's 23. And I think it's when you talk to the different states about how many wells they have in their states, I think 23 is a much better number and much closer. And even the 18 that the USGS proposes is too low. What we've seen. So
well, I'm going to use that as a quote. Thank you.
You're welcome. Well, what you did for Illinois is right on what we believe. We house the state's well logs. We work with them every day. We know we don't have all of them, but you mentioned different states have different rules when they started. I always use the example of Illinois started in 1968, And early on, drillers kind of weren't necessarily a fan of that, but overall, especially today, all of our drillers are on board, and we're getting all our well logs. But New York didn't start till 2000, so they know they don't have a lot of their information because of that. So,
I should say the value of how we did it was, a lot of people have done the same thing, try to estimate where private domestic wells are. I think one of the prohibitive factors was it's really a pain to go to all the states, collect their data, curate the data, combine it. Yep. It's a pain. And the last speaker also spoke to that as well. We went through the work to do that, and we kind of validated our model based on this empirical data, which some other studies just haven't done. So I'm more confident in our estimates because they're based on these well records.
Sure, and I mean, I remember meeting one of your colleagues who's retired. His name escapes me. At Jim, thank you, Jim Weaver, right? At a conference, it was probably 2016 or 2017, and you'd already started this work.
Yeah.
So
he presented our pilot work in Oklahoma.
Yeah. So. All right. Well, there's a couple comments in here for if you want to look through the chat. The other value is the mapping tool that's available. Folks can use that, right? They can get those coverages. They're all publicly available.
Yep.
And it's, there's a lot of power in, especially the census block data that we can all use if we're those of us that use GIS for a lot of our work. So thank you very much, Fran and Alex. And if anybody has any other questions later, we can get them to them. That's what we have for today. I do want to mention that tomorrow morning is the mastermind thing. And if you haven't looked, I put those up this morning, the questions, but they're all related to doing outreach and how the pandemic has affected things and how do we restart our programs and all those sorts of issues. So it's not only a chance for you to hear from others who may have had those experiences, but it's a chance for you to share your own programs, issues, and what you're trying to do there. And it's really valuable if we have a chance to really communicate all that. So I hope everybody shows up tomorrow in the morning for that. And we'll see you at 10 a.m. Central tomorrow morning. Thank you, everyone.